gonna record this. All right, loud and clear?
Yeah.
Yes, yes.
Okay, so let's do a very quick recap of what we did last time or yesterday, and also what we're going to do today. Last time we covered from the first 5 weeks, mostly, which is we first looked at what is software engineering, which is just software development. How do you split your project into 5 phases: analysis, what was it? I forgot. Analysis, design, implementation, testing, and maintenance. And we also looked at the different types of diagrams that we use in each of those phases to help communicate within our software development team what our software should do and how it should do it. So we basically looked at, first we looked at the use case diagram, which shows a rough overview of what the software package does. Such, our example was a banking application. So that's our software package. What are the functionalities and what users are involved? Okay, that was used in the analysis phase mostly because it helps us draw up an overview. Then we also looked at the activity diagram, which is when we don't look at the overview anymore, but we look at a specific activity that a user could carry out, could execute using our software. So we want to know the sequence, what happens first, what happens last, whether there's any branching, so any decisions that have to be made, yes or no, whether there's any parallel execution that will happen. So we looked at this, if you remember. Diamonds represent decisions, bars represent parallel splitting, and these square or ellipses represent actions that you could take. For example, make coffee, make espresso, whatever, okay? Then we also looked at a more detailed version or a more detailed diagram than the activity diagram, which was the sequence diagram, which still shows a chronological ordering of events that happen. But it doesn't only show that, it shows the details of each event and also exactly which users are involved or which actors are involved, such as the user, the Geldautomat, the bank server, and your bank account here. We said that there's 2 kinds of arrows here, the solid arrow and the dotted arrow. The solid arrow is just for any normal action that would happen. And a dotted arrow was a reply to a question. So if we look here, the verify card was a request and card OK is a reply to that request. Or card invalid is another possible reply to that request. That's why this is put in a box to show that it's an alternative. And we saw that this long rectangle here, it's called an Aktivierungsbalken, which just shows from when to when is that particular actor active during the process. Okay, then we also looked at a class or class diagrams, which we're familiar with from programming. We learned in programming how to write Java classes, how to write abstract classes in case you have different classes that share the same functionality and you don't want to copy paste those functionalities every time into each class. So you could write up an abstract class that has the common features and then have the child classes inherit those features from the abstract class. And we also recall that an abstract class cannot be instantiated. It can only list functionalities, but it cannot you cannot create an object of that class, okay? And we also reviewed interfaces, how we said an interface was like it's not supposed to be an object, it's supposed to be just a collection of methods that different classes might want to use, might want to share. And interfaces are useful when we don't want to create particular or concrete objects like we would with a child in an abstract class, but it's useful for us to help group together a bunch of methods that are used by many different classes. And the classes that want to use those methods can just implement the interface. Okay. An enum is just a special type of class that lists limited instantiation possibilities of a data type. So an enum is more like a data type. Actually, our example was days of the week. If we want to write a calendar program, we know that there's only 7 different days. We want to make it clear that it's days we're talking about. We don't just want to save it as a string. So we use an enum that lists Monday to Sunday. And that way, whenever you want to save the day of an event, you can just save it using the data type day instead of a regular string. And that way, Java or your computer knows that, okay, it's a special category of information, right? And we also explore the different types of relationships that classes could have with each other. Inheritance is the most intuitive one that we know out there. It's just a regular parent-child, just like class A extends class B, or class A extends an abstract class B. So class A would be the child, class B would be the parent. We know this. We also, I should probably change the ordering of this. I'm going to put associations down below. Yeah, we also, after inheritance, we look at compositions and aggregation, and how we said there's a slight difference between composition and aggregation. A composition is an ownership. Ownership means that B, which is owned by A, would have no meaning or purpose in your system if A does not exist. So B cannot exist independently without A. An aggregation is a different kind of relationship where B would still exist independently from A. So even if A did not exist, we would still have B. And an example of that was, we look at 2 examples. The first example was a company. Like a firm company is an aggregation of people because, yes, a company is made up of people, but if the company went bankrupt and ceased to exist, the people would still exist. But on the other hand, a company is a composition of accounts as in financial accounts and so on, capital accounts and all that stuff, because those accounts can only exist if the company exists. If the company ceases to exist, then the accounts also don't exist anymore. Or an example that's more closely related to basic day-to-day usage of computers is a text editor or any program basically in your laptop. A program could own a piece of memory, right? If you took BUS or operating systems, you would know that a program in execution is called a process, and a process is not just the code, but it also includes the resources that are assigned to that process, such as memory. And a text editor could own a memory buffer, okay? But a text editor could also use a file. So the difference between that is that a buffer is a composition because a buffer would not exist. It would have no meaning or purpose in the system if you do not have a text editor anymore. Once you quit your text editor, the memory is freed up, the buffer is gone. But when the text editor is closed, a file that you save would still exist in the system. So that's why it's an aggregation. Okay, and class diagrams look very familiar to us. It's got at the top, it's got the name. Then below that, it's got all the attributes of that class with the data type and visibility, Sichtbarkeit. And below that, it's got all the methods that you have in that class, again, with any return data types like here, and also the visibility. Okay. And we didn't cover feature diagram last time. I didn't get around to taking notes for the feature diagram. I'll have to get back to you guys on that later on. But today we're going to do the second part of the course, which is basically from, well, if my computer will cooperate with me. What's going on? No, it doesn't want to work with me. Okay, the second part is more, it's like miscellaneous stuff. It's not about diagrams anymore. We've covered most of the diagrams except for the feature diagram. And it's more about just the rest of, principles or just ideas surrounding software engineering, or things that a software engineer would be occupied with, would be thinking about, would come across in his or her daily life. So first, let's look at general design principles that we want to stick to when designing software. This is a typical exam question. It's most likely going to come up in the homework as well. So we should understand this properly. So when we design software, the idea is that we want a good piece of software. But what does it mean to have a good piece of software? Well, it should have the following characteristics, and when we design it, we should keep these principles in mind. Correctness means that it should do what we want it to do. And we can verify that through testing, through her calcul, and all these things. Okay. Understandability and precision means that not only should the user be able to understand how to use our software, but software engineers, programmers within our development team should also be able to understand what each other is doing. And that happens through good documentation. Adaptability means that you should design and program your software in such a way that it can be modified, updated, and adapted to new scenarios easily. Yeah, and the one we want to focus on probably most here is the idea of high cohesion and weak coupling. So in a software suite, it's usually made up of many classes, like Java classes, for example, and those Java classes could be put into different folders called modules. And what we want is that within the same class, we want to have high cohesion. High cohesion means that in that same class, anything that you used often, for example, if you have to, find out the modulo of a number often, or if you have to find the absolute value of a number often, then you would write that as its own method in the class. Not like every time you want to find the modulo of a number, then you copy paste the code in each different place where you need that. No, we want to group that into its own method so that it can be reused by other methods. Okay. In other words, the subparts of a class should have high cohesion with each other. The subparts of the same class should be highly dependent on each other, because this helps us write legible code and avoids mistakes. We can imagine that, for example, if somehow we test our code, something's wrong, the module doesn't look right, then we know exactly where the problem is, and we only have to fix the problem in one place, which is in the method, not in 10 different places and then check 10 different places, and depending on the method that they're in, it gets messy, okay? So that's high cohesion. Weak coupling means now we don't look within the class anymore, but we look between different classes. So different classes should depend on each other as little as possible. For example, you want to avoid calling a method that belongs to another class because that would mean that your classes are highly dependent on each other, which is not good because if you want to update, the whole point of a class is to represent a specific functionality, right? A specific part of your system. And if our classes are highly dependent on each other, that means that if something is wrong with one class, that will affect every class that depends on it. Or if you need to update or upgrade or modify one class, then you would have to modify all the other classes that depend on it, which is not good. It does not make your code adaptable, okay? So that means classes should depend on each other as little as possible because it enables easy maintenance and also debugging. If there's a bug, you can test and you can narrow it down to a specific class and then just fix that class. All right. Any questions?
Tonk, I have a question.
Yes.
The high dependency between the parts of the same class. This part, it is a bit vague for me. Could you please re-explain this?
Yes, thanks for asking.
Thank you.
So imagine you have a calculator class, okay? Your calculator should add, subtract, multiply, divide, find the modulo, and maybe the absolute value of some input.
Mm-hmm.
What would you do in your calculator class? You would write an add method, subtract method, and so on, right?
Yep.
And if you have to find the modulo, inside your modulo, how do you find the modulo of a number actually? You would use probably the division, some division would be involved in there as well.
Yeah.
Right. And when you write your modulo class, how would you perform division? Would you rewrite your code that does the division, or would you just call the division from the division method?
Of course, I will use a division method.
If you have to use division, for example. So
yeah.
That means that division is an example of a functionality of a task, an Aufgabe that you have to, that it's just reused a lot in life, and since it's reused a lot, it deserves to have its own little method out there. What you don't want to do is not write a division method and then just copy the code body and paste it into other methods whenever you need to do some division. Does that make sense?
This makes sense I understand what is high cohesion is. Okay. I didn't understand what is a high dependency between the parts. What we mean high dependence? I can't.
Yeah, high dependency means each method in your class, you should write methods in such a way that they depend on each other as much as possible. Or let's replace the word dependency with the
for example, if I
usage. Okay, sorry.
High use.
Yeah.
For example, as you said, for example, I want to write a modulo method. So when I use division method inside this, does it mean they are high dependent from each other?
Yes, because the modulo method depends on the division method. In other words, the modulo method uses the division method to help it.
Okay, but when we write the classes, for example, weak coupling, we should avoid this using other methods from outside.
Correct.
Yeah,
that's correct.
Okay, clear. Thank you very much.
Thanks for asking. And the reason I want to emphasize, the reason that we want high dependency within the same class, but low dependency between different classes is because the whole idea that we have classes is because we want to split our system into subcomponents, right?
As independent as possible.
Yes.
That's all.
You don't want to, like, if you have a car, you don't want like your music system to somehow depend on the engine or the wheel, because if this,
Yep.
then yeah, then why manufacture it differently, right? So yeah.
100% clear. Thank you too many times.
Welcome. Thanks for asking. Any other questions for this part?
No, it's fine.
Well, if there's any other questions at any time, feel free to interrupt, and we'll address that
Okay,
right away. Okay, so we know about design principles. We know how to, we have a rough idea of how we want to approach software writing. Now, the next part is a completely different thing from that. It's called the 4+1 architecture views, or Sichten in German. Okay, so the idea is this: whenever you have a software system, like a banking app, for example, that banking app, or even like a large software system like Windows Vista, Windows 7, all these operating systems and so on, they usually involve multiple people, multiple stakeholders. These stakeholders view the software from different perspectives. The user would have a different relationship to the software system than the programmer, for example, right? But they are all stakeholders in the program, in the software. The user needs to use the software and the programmer needs to program the software. So we want to make sure that our software is written in such a way that all the stakeholders can interact with it, reasonably, intuitively, and so on. And for that purpose, we have different so-called views of the software, different perspectives of the software. So it's called the 4+1 because there's 4 views plus one that's not really a view, that doesn't really represent a stakeholder. But okay, we'll look at that later on. Now, the 4 views are the logical view, the process view called the Ablaufsicht, the development or implementation view, also called the structure view, and also the physical view. Okay. The logical view looks at the functionality that the system provides to end users. End users means the people that actually make use of the software. So you are concerned with what can the software do for you. If you are a user, you want to know, what can I do with this piece of software? That's all I care about. I don't really care about how it's implemented and all that. I just know what I can do with it. So that state diagrams and class diagrams help me understand the software from this perspective. That is the logical view. So class and model, and yeah, it's a final of the analysis stage, of the stage where you find out what software should do. Another perspective is called the process view. In this view, you want to look at the dynamic aspects of the system. Dynamic aspects means the system processes and how they communicate with each other. In other words, when you start the software, what is the sequence of events that happen there? For example, when you start an operating system, which process gets booted first, the spawn, and all this stuff that happens there, and you want to see a sequence, a chronological order of things, and that's basically the runtime behavior of the software. And this helps you understand concurrency, what happens at the same time if you have concurrent system. a distribution, meaning that sometimes you have a distributed system. So what task would be delegated to one CPU, what task would be delegated to another CPU, and so on. And you can also assess the performance and scalability. How much system resources are you using at this time? Are you utilizing the CPU fully at the start? Can you fit in, squeeze in any more stuff to improve the performance and so on? So this is a process view, and usually it's represented by the activity and sequence diagrams that we saw yesterday. Okay. Another view is called the development or implementation view, and this is actually the programmer's perspective, because it's represented by component and package diagrams that we have not learned yet, and they also didn't teach last year and the years before. I doubt they will teach it this year. They briefly mentioned it, but didn't, like, there was no homework or exam questions or anything of the sort on it. The only question about this was describe the development view, and if you say the programmer's perspective, then you're good. The physical or deployment view is the system engineer. Well, what's the difference between a system engineer and programmer? Programmer writes the code, system engineer designs the architecture. In other words, he or she designs the classes, which modules your program should have, how to split the tasks up, and so on. So it looks at the topology of software components. So it's like you look more at layers of software rather than the code. So how components are related to each other, such as layers of an operating system. So if you've done BUS, you might have seen this before, even outside BUS, right? Any computer would have a hardware. This is the hardware. And then you have the kernel modules, the kernel system libraries, and then the user applications up here. Right, so this is a rough depiction of the structure or architecture of your operating system, which is your software package. So as the name suggests, it has to do with the physical view. It concerns the physical layer, so the hardware, as well as the connections between software and hardware. And it's represented by UML deployment diagrams, which we also do not learn. So those are the four views, sometimes also known as the gang of four. And the last one, the plus one, is called the scenarios. This is not like from a specific person's point of view, but it's just viewing different possible scenarios of how your software might be used. So it contains, a rough description of the architecture, just like with the use case diagrams that we saw earlier. Remember the banking app and so on. It describes interaction between objects and processes, just like we saw in the use case diagrams. Yeah, it's another view of the architecture, a more detailed view than, more like overhead view than the physical view, which more focuses on the hierarchy of code, in particular with relation to hardware. So yeah, it's also known as a use case view. Any questions so far?
No, I don't have.
Yeah, okay. Great. Okay, so that was that. Now the next part is, well, let's do this part last because it's the longest part. If you don't mind, I would like to talk about testing first. they're all independent, so you don't have to know one part to understand the other. Anyways, testing. You want to make sure that your software does what it should do. So you want to test your software. And in general, there's two kinds of testing. There's the black box testing, which is when you test whether your software does what it should do. So you basically look at your Sichten heft, at the specification. For example, the software should add. So then you try to add numbers and with your software, with your program, and see, does it add properly or not? And then you see, oh, it should subtract. Okay, then you test subtraction. Does it subtract properly or not? And so on and so forth. So that means that you don't actually have to know the code. You just have to know what your software should do and test it. And testing means that, for example, if you want to test the addition functionality, then you want to test addition with different types of values. For example, positive numbers, negative numbers, 0. Can it add 0 properly? Can it add positive numbers? Can it add a positive and negative number properly? Can it add, what happens if you add the biggest integer possible? What would happen? Would it overflow? Would it give you an error message? Would it, all these things, right? These things, these groups of numbers are called equivalence classes. Equivalence classes are just values with similar properties or value limits, such as, you know, the Grenzwerte of integer, so 2 power 64, 2 power 64 minus 1, and so on. And special values like 0, like null, and all that stuff. So that's black box testing. You don't care about the code, you just check whether it works. White box testing is when you actually know the code and you look at the code and you actually test your code line by line. There's 3 kinds of white box testing. The first kind, the easiest kind, is the Anweisung Überdeckung, which means you test each instruction. So each line of code one by one. See, does this line work? Okay. Does the next one work? Okay. Zweigüberdeckung is you test the branching. So whenever you have a switch, an if statement, all these things, you want to make sure you test the if condition, you test the else condition as well, right? And yeah, and the Pfadüberdeckung is the most complicated one, which is when you test every possible control flow path. I have to show that using an example from the homework. So bear with me for a while, please. Goodness. Let's see. Okay. Right. Okay. So, yeah, here what we have is, well, we should probably see the alphabet first. So here we have a method. It computes the absolute value. And we do not know the code, so that means we have to use the black box test. So yeah, and what values would we have to test there? Well, obviously we want to make sure we test the largest int value, the smallest int value, all the something from a positive int value, a negative int value, a special value such as 0, and a value that is greater than, that is over the limits of integer. And from each equivalence class, we don't have to test every single value from that class. We just have to choose a member of the class called a representant and feed it into the method and see if it works or not. Yeah. So for example, from the first equivalence class, the largest int value, we literally choose the largest int value, or the smallest int value for the next equivalence class. We pick a random positive int value, random negative int value. And when you do that, you basically test all the different scenario, like value types that could possibly affect your method. Okay. Guys, give me a short break, please. I'll be right back.
Okay, take your time.
Sorry about that.
No problem.
Okay. So that, I hope we understand what equivalence classes and black box testing means now. Any questions?
Tonk,
Yeah.
I have a question.
Yes,
Do we
please.
really need random numbers from, for example, positive and negative? Because we already checked this highest and lowest value. So it is just for additional example, or
Yeah.
we really need in this case?
In this case, well, let's think about it. Maybe together. Positive value. Yeah, I think we should, because in case there's a problem with a positive limit, it doesn't mean that there's going to be a problem with the normal int values, right? Or just because a normal int value works doesn't mean that the...
But it doesn't work in its grants, in its limit, yeah?
Yeah.
Do you mean? It can work for maximum number, but cannot work for maximum number, but it can work in any number.
Yeah,
Maybe, yeah.
something like that. Yeah.
Okay, okay, thank you.
Thanks for asking.
Thank you.
And white box testing, okay, we'll look at an example of that as well. So in white box testing, we actually have to look at the code. So a typical exercise would be they give you a code, and then you have to look at the code and see, okay, what is the control flow? And in order to understand that visually, we come up with a control flow chart, which looks like this, right? I'm going to split my screen and let's have that there. Okay, so, oops. Continuous scroll and here, yeah. So here's our code, right? And you see that the first part is just different individual instructions. So that's the first part, individual instructions. From there, you have a while statement. While statement means that you have to check a condition. That condition could be true or false. So that means you have a branch. So the condition is, this current char not equal thing. So you put that here in a diamond because remember, diamonds represent decisions. And if it's true, what will happen? If it's false, what will happen? And if it's true, well, it has to check another one, which is the if statement, another condition. So it goes there. If it's false, well, then it goes here and the program ends. And then if this if statement is true, you check the next if statement. And that if statement is represented by this one. If that's true, then what happens? If it's true, it goes here. If it's false, it goes here. We forgot to put that. And so on. And then you go on to the back. And then at the end, yeah, you go back here. And so this shows us a visual representation of our code. That helps us carry out the 3 different types of white box testing. Anweisungsüberdeckungstest just means that you have to call this method binary to decimal, call it with an input that would test each instruction line one by one. And if you put in 5, it would convert, it would test that, and yeah. Or so you're just testing from top to bottom, there's nothing there. Zweigüberdeckung means that wherever you have a branch, for example, here and here, here and here, here and here, you need to test all those branches. So if we take a look at, if we pretend to put in 5, well, if we put in 5, it would terminate. It would not convert it to a decimal number because it's already, it's not a binary number to begin with. If we put in 1 and 1 and we look through the code, it would do something like, it would run and it would run through through a branch once, and then it would, I don't know whether it takes this branch or this one. I can't be bothered to figure out now, but yeah. And there should be more tests to make sure that you test every single branch. So you test this and this, you test this and this, and you test this and this as well. Abfahrtüberdeckung is the most complicated test because you have to test every possible path you can take from start to finish. So that means you have to test like literally this path, you have to test this path, you have to test this path. You have to test, oops, oh no. Zoom is silly. Yeah, you test this path here, you test again this path here. So there's really a lot to test, and you just have to think about, okay, what are the inputs that would run through every possible path possible from start to finish. All right. Questions?
No.
Okay.
Oh, fine.
Sorry? So that was testing. It's a small section. The last largest section is design patterns, or Entwurfsmuster in German. Here, the idea is that if you're a software engineer or a programmer, a lot of times you're going to encounter similar problems in your program or similar tasks that you have to accomplish. Your tasks follow a familiar pattern. And so that's why some people have come up with general design patterns as a template. You know, like when you write a letter, a lot of times you just use a template maybe, and so on, so that you have the general structure, and then you just modify the little details in there. It's the same thing. Instead of a template for a Word document or for a wedding invitation, you have a template for your code. Okay, and there's a video that I really recommend everybody watch, or a playlist actually. The link is here. We don't have to know all the patterns in the video. We only have to know the patterns listed in this document or in the lecture slides. But nevertheless, do watch this when you have time. It'll help you understand it in depth. So the first kind of pattern that we were going to look at is called the adapter pattern. And we're familiar with this in daily life. An adapter is what? It helps one device work with another one if those two devices aren't compatible. Like when you go abroad, the plug in your wall is different, the electrical socket is different. So you bring a travel adapter with you to make sure that, to help you be able to get electricity from the wall to your phone. All right. So the same thing with software. Imagine I have a class. This is a regular class, okay? Any Java class right here. And I have another Java class right here. And I wrote them independently of each other. And for some reason, I find out later that, oh, this class wants to use something from this class, but it's not compatible. So I write another class called an adapter that helps convert this one, that helps to convert a request from this class into something that this one can understand. For example, maybe, in a method, you might have to put in some inputs. A method has a signature, and maybe this class doesn't know a specific data type. An enum doesn't exist here or something like that. But that enum is needed to make this method call work. So we have an adapter that puts it in and bridges the differences between two classes. The next pattern is called the observer pattern, which is, we also know this in daily life. It's like in YouTube. If I have a YouTube channel, maybe I have some subscribers, and so my observers or subscribers want to subscribe to my content, to updates from my YouTube channel, from my class. My subscribers are called the observers, and the class that's being subscribed to, such as my channel, would be the observable class. Okay, and there's two ways that you can follow somebody. You could, the subscriber could ask the observable every single second, do you have something new? Do you have something new? Do you have something new? And so on. With 1 million subscribers, that gets annoying. It crashes your system. We don't want to do that. It's inefficient. So instead of having the subscriber, or in other words, the observer, constantly asking data from the observable, it's better to have the observable push any updates to its subscribers or observers. Yeah. So that means the observable, the channel, the YouTube channel, has a one-to-many relationship with its observers, because one channel can have many observers, right? And here's how you would implement it. So let's try to understand what this means. What do we have here? First, let's look at only the top two, ignore the bottom two, pretend it doesn't exist. Here's my YouTube channel, and here are my subscribers. What would I do? Well, from my point of view, the observable, I'm being observed by other people, so I want to know who I have to broadcast to, who my subscribers are. So I need to have the function add observer. So in other words, add subscriber, delete subscriber, and notify subscriber. Because those are basically my tasks, what I have to do to communicate with my subscribers, right? And my subscriber just has to listen for news whenever whenever the subscriber receives an update, then it should go, here's an update, and take note of it. That's all. So that's what the update function does, right? And so this shows, remember, an arrow like this is a has a relationship. An observable has a observer. The star means many observers. So one observable can have many, one to many observers. Okay. But now this is only the functionality that enables this subscriber relationship. These two are usually implemented as interfaces. So they're not concrete objects, concrete instantiations. And they just provide the subscriber functionality to concrete classes, which you see down here. Okay, so what you see down here is actual concrete instances of an so a subject is an observable. It's a concrete instantiation of, not instantiation, sorry, but it's a concrete implementation of the observable. And concrete observer here is a concrete instantiation of an observer. It doesn't have to be, these two up here don't have to be interfaces. They can also be abstract classes. It depends on your liking and the situation. But the whole point is that you split the functionality, the subscription functionality into its own interface, so that no matter which channel or no matter what kind of subscription relationship you have, you can just use it. You can just pull these methods from the interface instead of having to write it in your concrete class. All right. Yeah. Does that make sense? This big arrow here means it's an inheritance. It's an a subject is an observable, a concrete observer is an observer, and an observable has observers, that's shown by this arrow, and a concrete observer has a subject where it gets updates from. Okay. Does that make sense?
Yeah.
Kind of, yeah.
Yeah.
I think it's better to watch the videos.
That's
yeah?
correct. Yes,
Yeah, yeah.
I recommend the
Because
videos. Really.
Yeah, I remember last year I watched these videos. So
it's great. Great guy.
really helpful. Yeah, great.
Yeah. The next pattern is called the singleton pattern, which is you use it when you want to make sure that your class can only have one instantiation globally. For some reason, I don't know why. A lot of people think that singleton pattern is dangerous. It's not good practice, but we don't care about that. We just care about what it is. And so here's how it works. Ignore this. Let's look at here. It's a screenshot from the video. The singleton pattern basically prevents you from creating more than one instance of your class. So you do that very simply by this attribute. So you first have a static attribute of type singleton called instance. Type singleton means this instance is your one global instance of your singleton of your class. Okay, and static means there's only one. In the entire class, for this entire class, there's only one possible singleton. Okay, and that's here. And then you make it private because you don't want other classes to be able to modify this instance. So they would not be able to create another singleton instance or another instance of your class and say, oh, this is my new singleton instance. No, that's not possible because it's private. Nobody can touch it. The constructor is private to prevent outsiders from creating additional instances. Then, of course, you also have a method so that other classes that might want to communicate with this singleton, with this single instance of your class, have to do it through this method It's not a private method, meaning other classes can access it. It's a static method because it's called on the class. So you would do singleton dot get instance, right? And this get instance basically just returns you this instance of your class. Does that make sense?
Yes. Yes.
Really?
Yeah.
Philip, Zorali?
Of course, it's fine.
Yeah, kind of. But as I said, I need to watch the videos.
Okay. Yeah, definitely watch the videos, please.
Yeah.
All right. Another one is called the decorator pattern. And the decorator pattern, what it does is it adds additional functionalities to an existing class dynamically. Okay, what does that mean? Dynamically means that you can modify the behavior of your class during runtime. While you're using the program, you can modify the behavior of your class without having to change the source code, without like literally opening your class file and, you know, editing the code. Let's look at an example. It's better to understand from there. Imagine I own Starbucks, and Starbucks, you know, you've got so many different types of beverages and so many different variations of each beverage. You could have espresso with caramel, espresso with soy, and all these things. I don't know. I don't go to Starbucks. Okay. What you don't want to do is you don't want to create different individual classes for espresso with soy, espresso with caramel, espresso with honey, espresso with foam. I don't know what different types are there. Because if you do that, well, this is what your program is going to look like. You're going to have an explosion of classes. We don't want that. This is the parent class that, you know, has like the add milk, the compute costs of the drink and so on, that's shared by all these classes, but we don't want to have so many child subclasses. Not good. Okay. So how do we get around that? Well, we look at this idea. Imagine this is the parent class with the basic functionalities, right? So like it's my espresso class, for example. My espresso class, I should have the option of adding caramel, adding soy, and all these things. And I want to do that by first making an espresso, then adding the soy, then adding the caramel, and so on. I don't want to, yeah. So basically, I first execute this class, and the result of that is then modified by this wrapper, and then modified by this wrapper, and at the end, I have espresso with caramel and soy. And the way you do that is you use the decorator pattern. So here's how it works. At first, you just write a rough abstract class. This is abstract, by the way. Abstract class beverage, get description, and compute the cost, let's say, right? And let's say I only have two kinds of drinks, espresso and decaffeinated coffee. And of course, I mean, both of them implement they have different costs. So they have different versions of the cost function, but the get description is probably the same or something like that. Yeah. Now I want to make sure that both of my drinks also have the additional option of adding caramel syrup or using soy milk to make the thing. And I do that by using this decorator. This is the decorator here. What it does is as follows. You write up a separate class called the add-on decorator. Okay. And the add-on decorator is inherits from the beverage class, sure, but it also implements, or no, it also has a beverage in it as well. So it is a beverage, but it also has a beverage. It's a bit confusing, I know, but the idea is that now what happens is whenever I instantiate this class, right? Whenever I instantiate this class, I have to have another beverage that's related to my decorator instance. So that would mean that since this is an abstract class, there's no such thing as a beverage on its own. A beverage is either a decaf or an espresso. So my decorator would have to have an espresso object. And an espresso object has all the constructors. So first you would brew your espresso. And then your decorator object would also be a drink in itself, a beverage in itself, and it would call any additional functions that could add to the espresso object. Okay, so that's why caramel and soy are now written as subclasses or like concrete instantiations of an add-on decorator. Oh, this is an abstract class as well, I should mention. And that just means now that I do this, I can now instantiate an espresso and a caramel always is related to either a decaf or an espresso. And that allows me to combine the properties of these two classes without having to write espresso with caramel class and then espresso with soy class, decaf with caramel, decaf with soy. Does that make sense?
Yeah, concept is clear.
Yeah, the implementation details, I don't know that well either. Please check that out from the video. The lecture slides are terrible. So I would start with the video first. Okay. And yeah, so that's how it would work. You have an abstract component, a concrete component, and a decorator that allows variations or add-ons to your concrete component. Yeah. Then there's the composite pattern and the factory method pattern, which I didn't get time to take notes for. So please watch that from the video.
Okay.
I think this is probably the most ambiguous part of Softwaretechnik. But if you watch the video, things will become a lot clearer. Do a few exercises, you'll be confident for the exam. Okay. Questions?
As I remember, in exams they only ask which pattern is that, yeah? Which pattern does it belong? Or
yeah, I think they also ask you to draw it. Draw the factory pattern, yeah. So you have to memorize all these
yeah, clear.
All these graphs. Okay.
I remember, yeah. Okay, thank you.
Yeah, thanks for asking, good point. All right. And the last part, I almost finished, but I was running late, but never mind. Software product line, it's completely unrelated to everything else. The whole idea of this is just that if you create software, obviously you want to upgrade your software as time goes by, rather than going back and designing everything from zero. So just like Microsoft did 95, 98, I mean Windows 95, 98, XP, Vista 7, 8, and now Windows 10. That's what you want to do, right? As well. Software has updates. And the advantage of that is when you do that, you have lower costs, lower complexity in maintenance, and you can have higher quality software overall because you can learn your lessons from the previous version and improve on it. And there's two kinds of software product line engineering. Again, a super fancy name for what should be a simple concept. Software product line engineering is just how you want to plan out the evolution of your software. The two different areas of software product line engineering are the domain engineering and application engineering. In domain engineering, you determine the scope. What kind of tasks should your software support? If you try to make your software too universal, it can do everything, it's Superman, super software, then the problem is that your components are going to have low synergy between them, which means that they won't be closely related to each other. It doesn't make sense to, just like the Microsoft Office package, there's Word, PowerPoint, Excel, and so on. And there's a reason that they're split into different software, different programs. It would be so complicated if you put all the functionalities within one program. Nobody would want to use it. A lot of those components would have nothing to do with the other ones, like the animation feature from PowerPoint would have nothing to do with Excel or Word, for example. So that's why, yeah, you should determine a suitable scope. That's important. And if your scope is too narrow, then you can't really create a lot of new products from your software or from your foundation, from your platform. And in domain engineering, they like to use feature diagrams, which describes possible variations of a software product. We'll have to go over the feature diagram later on. Application engineering, I don't know. Thank you for your attention. Goodbye.
Thank you very much.
Any questions?
Actually,
Yeah.
it was very clear for me. Thank you very much.
Oh, somebody's chatting.
It was me. Never mind.
Okay. So, well, I should probably show you what we did with respect to the lecture. So the lecture, they split it into from part 1 to part 13. And the thing with Softwaretechnik lectures is that they're so poorly constructed that more than half of the things on the slides are things that don't make sense even when they explain it, and you never have to know, you never have to use, or they're things that you know anyways. It's like the most basic common sense that 8-year-old child knows it, but they still write it in a way that makes it seem complicated. For example, okay, this part is okay. So this was slide 2 on the analysis part that we covered last time. And so on. And yeah, like these slides are crap. A lot of the slides have nothing to do with the homework, the exam. So my personal opinion is that there is no use in watching the lectures. The most useful thing you can do for yourself is 1, do the homework, 2, look at previous year's homework and how it was done, and 3, watch the YouTube videos on design patterns. If you do that, you can get a 1+ in Softwaretechnik already. Some slides are useful, but a lot of slides, like, for example, yeah, this entire part, there's so much junk in there. Like, it's beyond words. I don't know whether they're drunk when they made this or something, but yeah, feel free to skip it. Yeah, that's all. So we covered basically from part 1 to part 7, and I didn't. The last part that we left off was the software product line, application engineering. That belongs to the generative software Entwicklung part. That's it. The last parts are not important. So, yeah. And if you guys have any questions, ask in the group, or whoever wants to do the homework together and discuss things, the details, we can do that as well. All right.
Yeah. Okay.
Okay. Okay. Yeah.
Nice.